Today in this class, I would like to explain about solutions part 2, solutions. In this today, I would like to discuss about solubility. Solubility. So, what is meant by solubility? Suppose if you take water in it, add some glucose, then what happens? Some amount of glucose is soluble in the water. If you add still more amount of glucose, it will soluble up to certain extent. Even still more glucose is added, it won't soluble. So, in any solvent, if solid or liquid solute is added, it is soluble to certain extent. So, solubility means the maximum amount of solute that must be present in certain amount of solvent is known as solubility. This solubility is calculated by using mass of solute by mass of solvent into 100. By using this expression, we will calculate the solubility of solutes. In this class, let us discuss about the solubility of solid solutes in liquid solvent. Number 2, solubility of gases in liquids. Number 3, solubility of liquid in another liquid. These 3 types of solubilities we have to see now, one by one. If we talk about solubility of gases in liquids, here this solubility is explained by a law called Henry's law. Henry's law explains the solubility of gases in liquids. Whereas these 3 types of solutes, when dissolved in liquid solvents, how they behave, that can be explained by using Raoult's law. By using Raoult's law. What are the factors that can affect the solubility? Main factors that can affect the solubility are: number 1, nature of solvent and solute. Number 2, pressure. Number 3, temperature. The factors that affects the solubility of this solid into liquid are nature of solute and solvent. Suppose take some water, this is water which acts as solvent, and add some amount of sodium chloride into this solvent. Whereas take another solute, naphthalene, add in it. Sodium chloride is only soluble in water, whereas naphthalene does not soluble in water. Why? Because sodium chloride is ionic compound, whereas water is a polar solvent. So ionic compounds are soluble in polar solvents. Polar compounds are soluble in polar solvents. Since naphthalene is non-polar substance, it is not soluble in polar solvents. This is nothing but like dissolves like temperature. If solutes requires heat for solubility, that means delta H of solution, enthalpy of solution is positive. The enthalpy of solution is decided on the basis of lattice energy of the substance and also its hydration energy. Enthalpy of solution is the sum of lattice energy of the solute and hydration energy of the solute. Lattice energy is the required amount of energy, so positive, delta H is positive. Hydration energy is released amount of energy, that is negative. Solutes such as glucose, such as sodium chloride, etc., their lattice energy is more, that means positive value is more than hydration energy. So in this case, the enthalpy of solution is positive. In such type of solutions, temperature rises, solubility increases. There are second kind of solutes. Solutes solutes does not require temperature for solubility. In this case, enthalpy of solution is negative. Why enthalpy of these solutes are negative? Because if you take examples like KNO3, ammonium chloride, NaNO3, this type of salts, their lattice energy is less. Lattice energy is less than hydration energy. For the solubility of these kind of salts, temperature no need. That means temperature increases, these salts solubilities decreases. And when we talk about effect of pressure, almost nil. Effect of pressure is almost no effect. Pressure has no effect on the solubility of solids, because solids are less compressible. That's why pressure has no effect on their solubilities. The factors that affects the solubility of a gas is mainly nature of solute. That means if a gas is easily liquefiable, then that gas is highly soluble in that given solvent. Easily liquefiable gases will soluble more than the gases which doesn't liquefy. For example, carbon dioxide is easily liquefiable gas than helium. Therefore, carbon dioxide is highly soluble in water than helium. This is because why? Carbon dioxide is easily liquefiable gas and it's having more surface area, more van der Waals forces, and that can easily soluble in the water rather than the helium. Effect of temperature on the gases solubilities in liquid. Every day we are observing, if the liquid in the vessel gets bubbled when it is heated on a flame. Every day we are observing, when a liquid is heated, then whatever the gases are soluble in the liquid, they will come out as bubbles and they will escape out from the vessel. That means temperature increases, solubility of gas in that particular solvent decreases. This can be applied to any type of gas. And third one is effect of pressure. Effect of pressure on the solubility of gases. Pressure plays important role on this kind of solubility. We know in the market, Coca-Cola, Thumbs Up and all, they are packed with say this is Coke. They are packed with high pressure. This is the liquid in which carbon dioxide is passed at high pressure. The moment when we open the lid of the bottle and if you transferred it in a glass, immediately we'll observe a froth. That froth will comes out of the glass. That's what we observe regularly. This is happening why? As the moment when you open the lid, the carbon dioxide comes from high pressure to low pressure. So, gases always diffuses from high pressure to low pressure. That's why whenever you pour this Coke in this bottle, the carbon dioxide escapes out because the external pressure and the carbon dioxide pressure is less. External pressure is less. Pressure of the gas is proportional to solubility of the gas. Pressure of the gas is proportional to solubility of the gas. Henry's law explains the solubility of gas in the given amount of liquid at that given temperature. According to Henry's law, the pressure of the gas that is going to be soluble is directly proportional to solubility of the gas. Pressure of the gas is proportional to solubility of the gas in the liquid. Pressure of gas in vapor phase is equal to a constant kH into solubility. Generally, solubility is expressed in grams per liter like that. So, grams per liter, if you write pressure of gas is equal to a constant into concentration of the gaseous solute in liquid. If the liquid is having more gas, the fraction of gas in the liquid will be more. So, the equation let us write as pressure of the gas equal to kH into more concentration means more mole fraction of that gas in the liquid. Now, we have an equation, pressure of the gas is equal to kH into mole fraction. Pressure of the gas means P gas means pressure of gas in vapor phase. kH is what? It is Henry's law constant. This is the mole fraction of gas in the given amount of liquid. This Henry's law is a temperature coefficient. Henry's law constant is a temperature coefficient. For example, the mole fraction of the gas is equal to 1, then the pressure of the gas is going to soluble in the liquid is equal to Henry's law constant. The units of Henry's law constant is equal to, since it is a temperature constant, Kelvin, and it is a pressure are expressed in bars. These are the units of Henry law constant, Kelvin bar. Since it is temperature dependent, when temperature is raised, the gas which is present in the liquid escapes out. So, X gas value decreases. To equalize this, the KH value increases. So, temperature increases, the KH value also increases. That is why it is temperature dependent. This Henry's law, when we talk about the limitations of Henry's law, Henry's law is applicable to the gases which are not reacted with the solvents. If the gas reacts with the solvent, for example, carbon dioxide passed into water, then carbonic acid is formed. For that kind of solutions, Henry's law doesn't account. So, Henry's law is limited to gases which does not react with the corresponding solvent. This Henry's law is applicable to the gas in liquids solubility at low pressures. At high pressure, Henry's law does not proves. So, gases with low pressure when dissolved in water only, Henry's law is applicable. So, what are the uses of the or applications of the Henry's law? Here the bottle is sealed at higher pressure. So, in the bottle carbon dioxide solubility is more. Pressure of the gas increases, its solubility also increases. Here more pressure, more solubility of CO2. The moment when you open the lid, then what happens? Carbon dioxide comes from higher pressure to lower pressure. So, when you pour into it into a glass, the pressure of carbon dioxide is very less because of less pressure here. So, carbon dioxide comes out as in the form of bubbles. Let us see another application of Henry's law. Scuba divers. Scuba divers means whom? The divers which goes to the underneath of the sea and do some experiments. So, they will carry a cylinder. It consists of nitrogen and oxygen, that means air. Along with that, they will carry 11.7% of helium gas also. Why? Here, if you observe carefully, this is the sea level and this is a mountain. This fellow is a mountaineer. He is at the hilltop. So, at this area, here to here, at this mountain top, low pressure of the gas. At sea level, some pressure is present. If we move, if the scuba diver moves down, still you can experience more and more pressure. So, once again, here at the hilltop, pressure is less. At the sea level, pressure is intermediate. At the bottom of the sea, pressure is high. When this scuba diver goes down and down, then because of more pressure of the gas, solubility of N2, more pressure of the gas, the N2 solubility in the blood increases. When he comes up to the sea level, when he moves up, then what happens? The pressure little bit decreases. Now, what happens? Let us see. If he moves downward, because of more pressure of air, more nitrogen is soluble in blood, which is toxic. When he moves upward, when he comes to the sea level, whatever the gases soluble in the blood comes out as bubbles, and suppose this is the blood vessel of a human being. When he moves down, more nitrogen is soluble in the blood. When he moves up, whatever the nitrogen and oxygen soluble in the blood, they comes out in the form of bubbles. So, bubbles are formed in the blood vessels and they block the capillary action of the blood vessels. The third application of Henry's law is climbers. Climbers carry oxygen cylinder for medical emergency, otherwise they will occur a symptom called anoxia. Anoxia. What is anoxia? Let us see. If the climber is at the top of the hill, he will experience with low pressure. At low pressure, the gases will be soluble in the blood will be low according to Henry's law. Pressure is more soluble. That's what observed in the scuba diver. In hilltop, pressure is less. So, because of less pressure of the gas, less oxygen is soluble in the blood. That will lead to a disorder called anoxia. So, because of less soluble of oxygen gas in the blood, he will goes into a symptom such that he will not think properly. Such condition is known as anoxia. To avoid the anoxia, extra cylinder of oxygen must be carried with high pressure so that he will get rid of this. So, these three are the applications of Henry's law. This question was given in IIT 2009. Here, this problem is based on Henry's law. We all know that pressure of the gas, partial pressure of the gas here is how much? Partial pressure is equal to mole fraction of the gas into total pressure. That's what partial pressure. Henry's law states that partial pressure of the gas is equal to Henry's law constant into mole fraction of that gas. Here, pressure of the gas, air contains 0.8 mole fraction of nitrogen, the rest would be oxygen. Oxygen mole fraction is 0.2. Here only nitrogen mole fraction was given. So, for partial pressure, substitute nitrogen mole fraction is 8 into dissolved in 10 moles of water at 5 atmospheres pressure. Total pressure is how much? 5. This what is equal to partial pressure of the gas. And in this question, Henry's law constant means Kh, that was given. How much? 1 into 10 power minus 5. First, we have to find out the mole fraction of the N2 gas in the solution. Let us find out. Mole fraction of the gas, N2 gas, is equal to 0.8 into 5 by 1 into 10 power minus 5. That is equals to 4 into 10 power 5. Sorry, this is 1 into 10 power 5. So, here also 1 into 10 power 5. This will gives to 4 into 10 power minus 5. Mole fraction has no units. Here, the number of moles of N2 from air dissolved in 10 moles of water is asked. This is per 1 mole. In 10 moles of water, number of moles of N2 dissolved is equal to 10 into 4 into 10 power minus 5. That would be 4 into 10 power minus 4 moles. So, first option is correct. Raoult's law explains the type of solubilities of a liquid into another liquid. For better understanding of Raoult's law, about vapor pressure we have to study. In this, liquid is taken, and here to measure the pressure of the gas, manometer, it is the mercury. Say this is pure liquid. In the pure liquid, the molecules which are present in the surface is having more kinetic energy than the molecules which are present in the bulk. As at a given temperature, the liquid phase is converted into, this is the vapor phase. The process of conversion of liquid into vapor state is called evaporation. So, this process, the process of conversion of vapor phase into liquid phase, is known as condensation. At a particular point of temperature and time, constant number of molecules in the liquid phase and constant number of molecules in the vapor phase is maintained. That particular time, rate of evaporation is equal to rate of condensation. At that stage, the constant number of molecules in the vapor state creates some pressure over this liquid surface. So, now let us see what is vapor pressure. The pressure exerted by vapor on its own liquid surface when the vapor phase and liquid phase are in dynamic equilibrium. So, at dynamic equilibrium what happens? Rate of evaporation is equal to rate of condensation. The liquid here is having the molecules whose kinetic energy is less. So the pressure of the gas, the pressure of this gaseous phase is nothing but the difference between the two levels of mercury. This is the vapor pressure. The difference between the two levels gives the vapor pressure of the liquid in the gaseous phase. So, is it clear? What is vapor pressure? The pressure exerted by vapor on its own liquid surface at a given temperature is known as vapor pressure. On what factors this vapor pressure depends? On what factors the vapor pressure depends? Number one, nature of solvent. Generally, liquids gives more vapors and some liquids gives less vapors when they are kept in a container. The liquids which gives more vapor at a given temperature T are called volatile liquids. Volatile liquids. Example, petrol, benzene, ether. They are volatile liquids. The liquids which gives less vapor pressure at that same temperature are called non-volatile liquids. Example, water, aniline. Non-volatile liquids gives less vapor pressure. Why volatile liquids gives more vapor pressure? For example, if you take ether, this is another ether molecule. The force of intermolecular force of attraction in ether is weak, so that the molecules from the liquid phase easily escapes out as vapor phase. Whereas water is non-volatile liquid because between water molecules hydrogen bonding takes place, so that the molecules will not escape out from its liquid phase into vapor phase. So volatile liquids have more vapor pressure. Non-volatile liquids gives less vapor pressure. So what does the Raoult's law says? The vapor pressure of a solution is directly proportional to mole fraction of the solvent. Vapor pressure of solution PS directly proportional to mole fraction of solvent. So vapor pressure never depends upon the solute because it is non-volatile solute. The vapor pressure of solution is equals to a constant into XA. Consider if you take a pure liquid, in pure liquid only XA is present, so its mole fraction is 1. If XA is 1, then vapor pressure of solution is equals to a constant, that is equals to, since the only pure liquid is there, its vapor pressure of pure liquid is taken as P naught A. Therefore, Ps is equal to P naught A into XA. This is the Raoult's law for the solutions containing non-volatile solutes in volatile solvent. What does it mean? This is vapor pressure of solution. This is vapor pressure of pure solvent. This is mole fraction of solvent. If you plotted a graph between vapor pressure and composition for that liquid, since only one pure liquid is present, here XA is equal to 1, here XA composition is 0. If only one liquid is taken in a vessel, the vapor pressure of that liquid is called as P naught A. So, this is the P naught A. As composition of or mole fraction of A decreases, if mole fraction of A becomes 0, the vapor pressure also becomes 0. So, vapor pressure of pure liquid proportional to mole fraction. So, this graph represents how does the vapor pressure of pure liquid decreases with the decreasing of mole fraction. Raoult's law for a solution of two volatile liquids A and B. This is volatile liquid A, this is another volatile liquid B. The mole fraction of this liquid is XA in liquid phase. Here mole fraction is XB. The pressure exerted by A vapor on its liquid surface is called P naught A. The vapor pressure of B liquid on its liquid surface is P naught B. Now, these two liquids are mixed in a container. Now, the solution of AB is formed. In this solution, some A particles and some B molecules will come as vapor. According to Raoult's law, the vapor pressure of each component is directly proportional to its mole fraction. Vapor pressure of each component in a liquid mixture is directly proportional to its mole fraction. For instance, PA is directly proportional to XA. That means PA is equal to P naught A into mole fraction of A liquid. Similarly, vapor pressure of B solution in the mixture is directly proportional to XB. That means vapor pressure of B solution in the liquid mixture PB is equal to P naught B into XB. Now, vapor pressure of this AB solution PS is equal to PA plus PB. That means total vapor pressure or vapor pressure of this liquid formed by AB components is equal to, instead of PA, we have to write P naught A into XA plus P naught B into XB. PS means what? The pressure of AB liquid on its liquid surface, vapor pressure of AB liquid on its liquid surface. This is nothing but P total. Total pressure is equal to partial pressure of one component A plus partial pressure of another component B. So this is used to measure the total vapor pressure of two volatile liquids. If you try to draw a vapor pressure composition graph, composition is increasing like this. Composition of first component, mole fraction of first component A is 1 here, and XA is equal to 0. If only one component is present, its vapor pressure is taken as P naught A. As the mole fraction of that component in the solution decreases, its vapor pressure also decreases in this direction. If XB is 0, here composition of B component is 1. Only pure B liquid is taken. It is having a pressure of P naught B. This is the vapor pressure of pure liquid B. As the B composition is decreasing in this direction, its vapor pressure also decreases. Now, the total pressure, total vapor pressure of AB liquid mixture is equal to this linear graph. So, total vapor pressure PS is equal to PA plus PB. This is what? This is the partial pressure of A component, that will be equal to P naught A into XA. This is partial pressure of B component, that is equal to P naught B into XB. So, in this vapor pressure versus composition graph, we understand that if the two liquids are volatile, the total vapor pressure of the liquid is maybe higher or maybe lower, that depends upon the composition of the components in the liquid mixture. Who can follow the Raoult's law at all conditions of temperature are known as ideal solutions. Ideal solutions. Now, if you look at the graph, the vapor pressure of the component is linearly dependent on its composition. Vapor pressure of any component is linearly dependent on its mole fraction. And one more thing, it is clear that here in this case, vapor pressure of B component is more than vapor pressure of pure A component. Now, why this Raoult's law is more advantageous, or it is having wide range of application over Henry's law? Because this vapor pressure of the solution can be calculated with respect to the mole fraction of A component and also with respect to the mole fraction of the B component. So let us calculate the total vapor pressure of the liquid mixture in terms of A component. The total vapor pressure of the solution can be related to either mole fraction of A or mole fraction of B. This is the pure liquid A and its vapor pressure is P0 A. This is the pure liquid B and its vapor pressure is P0 B. This is the liquid mixture containing AB components. In the liquid phase, this is liquid phase and this is a vapor phase. The mole fraction of A component is XA and mole fraction of B component in liquid phase is XB, whereas mole fraction of A component in vapor phase is Ya and mole fraction of B component in vapor phase is Yb. According to Dalton's law of partial pressures, total pressure is the sum of the partial pressure of A liquid and partial pressure of B liquid vapors. Now, P total of the solution is equals to P0 A into XA plus P0 B into XB. So, if the total pressure with respect to mole fraction A is considered, if XA plus XB is equal to 1, then XB becomes what? 1 minus XA. So, substitute 1 minus XA instead of XB. Now, P0 A into XA plus P0 B into, instead of XB, write 1 minus XA. So, P0 A XA plus P0 B minus P0 B into XA. So, P total is equals to P0 B plus P0 A minus P0 B into XA. Similarly, if I can calculate the total pressure with respect to B component. So, P total is equals to P0 A XA plus P0 B XB. Instead of XA, substitute 1 minus XB. So, P total is equal to P0 A into 1 minus XB plus P0 B into XB. we can write P naught A minus P naught A into XB plus P naught B into XB. Therefore, P naught A plus P naught B minus P naught A into XB. This is the total pressure of the liquid with respect to mole fraction of the B component. In this way, the Raoult's law is more advantageous than, and it is having wide range of applications than Henry's law. Now, basing on this, we can calculate the composition of the vapor in the vapor phase. This is the vapor phase. So, composition of the component A in vapor phase is calculated Y1, YA. YA means what? Composition of mole fraction of A component in vapor phase is equal to partial pressure of A by total pressure. Partial pressure of A means what? P naught A into XA by total pressure of the solution means what? P naught A XA plus P naught B XB. Similarly, the composition of the B component in vapor phase, component B in vapor phase is PB by P total. That means what? P naught B XB by P naught A XA plus P naught B XB. In this way, we can calculate the composition of the A and B components in vapor phase also. In this session, I completed the solubility of various gases, liquids and another liquids in another liquid, Henry's law and Raoult's law. So, hope you enjoyed very well. So, thank you.